So hello and welcome again. Today we are going to proceed to the analysis of structures. As defined, it is the process by which we determine how loads applied to a structure are distributed throughout the structure. Okay, for this reason, we are going to analyze the structure so that we can know the behavior of the structure when it is subjected to certain loadings so that we can appropriately design it accordingly. So these structures are usually joined through a pin. So we have a pin connected structure here. It could be welded or bolt connected. And as for the common types, we have number one, truss and frames. So these members are joined so that the internal force in the bar is directed along the axis of the bar. So in a way, the structure are carrying an axial load, or the member will carry axial load. So let me revisit you on the structure wherein there will be a rigid structure or a mechanism of structure that is uh, unstable. We have two structural systems here. So for the first, you can see on the left, it is having a mechanism that it is rigid because it is supported by three force members. So on your right, there are 4 pin connection on this system, so it will have a mechanism of instability. So there are two methods of analysis. We have method of joints, which applies the principles of concurrent force systems. So therefore, we are just limited to summation forces x is equal to 0 and summation forces y is equal to 0, because we do not have any distances because the forces are concurrent to each other at a certain joint. So the principle is isolation of joints. So for the other type of analysis, we have method of sections. So in this type, we are now considering a non-concurrent force system. So therefore, it involves three equilibrium equations, namely summation forces x is equal to 0, summation forces y is equal to 0, and summation moments is equal to 0. So here we will be considering the moment arm or the distance. So let us have now the analysis of trusses. Trusses is defined as a series of rigid frames fastened together in such a way as to resist change in shape to support a larger load having a longer span. So practically, these members will carry the external loading in a way that it will be transmitted along their axis or along the axis of the members. So with this, the bending is controlled. So therefore, the low loadings is just the axial, either tension or a compression loading. So let us now have example starting from method of joints. So let us have here a complex truss loaded with pointed loads as shown. So it is supported by a roller and a hinge with other forces, labels, and angles. Working with this, practically we first establish the free body diagram indicating the reaction. So it is observed that this truss is symmetrically loaded. So if we're going to add all of the loadings, we have 7,000 all in all, and that will be just carried or equally carried by reactions at A and reaction at G. So RA and RG would have 3/5 each. Okay, so I know you have already done this in your statics, wherein you are going to isolate the joints and then label the joints and then solve for the unknowns, solve for the components, and come up with the force member. So this time we will have a different approach on that, but the same principle. However, we are going to directly work with the whole structure. So for the whole structure, let us just bear in mind that diagonal members have its horizontal and vertical component, and vertical component supports only the vertical axis, and the horizontal members will just support only the horizontal axis. Just the same procedure, we are going to isolate joint per joint. Of course, the first step is to choose the joint where there are only two force members. Practically, if we look into the truss, A and G has the joint where two members are present. So let us reduce the angle so that we can work with the truss cleanly. So starting at point A, we could see here at point A that there is a 3,500 going upwards. So if we take a look at the members which will be responsible to resist the 3,500 going upwards, AC has nothing to do with 3,500 because, as we have said, horizontal members are for horizontal axis, and diagonal members could be resisting, or this actually resisting horizontal and the vertical axis. So this joint 3,500 is to be resisted by AB only. And again, AC has nothing to do with 3,500 because AC here is horizontal force and 3,500 is a vertical force. So basically, the AB will counter this 3,500. So we draw the force triangle on the diagonal member, place the horizontal and vertical slope, which is ABY and ABX. So among the two, only ABY is involved in 3,500. Again, ABX has nothing to do with the 3,500 because that is horizontal. Therefore, we can rationalize our direction here. We do not need to assume anymore because we are sure that 3,500 will be only resisted by ABY. So therefore, we draw an arrow. This is now the arrow directing ABY to contradict 3,500 because if this is the inclined force, of course, the vertical component ABY is towards that arrowhead. So therefore, it is going downwards. And what will be the magnitude of that downward force? It is ABY is 3,500. So knowing that, we can also obtain ABX because we have the slope. We'll just write tangent function. Tangent 30 is equal to ABY all over ABX. We set ABY equal to 3,500. Therefore, ABX is equal to 6,062.18 pounds. Knowing ABY and ABX, we can already obtain AB, or the force member for AB. We'll just have to have a Pythagorean theorem for that. So we have AB is equal to square root of ABX squared and ABY squared. So therefore, performing this equation, we have AB to be equal to 7,000 pounds, and this shall be in compression. So upon obtaining AB, of course, our vertical was already balanced. However, if we look at the horizontal axis on A, still we do not have balance on AB. Why? Because by placing ABY equivalent to 3,500 to counter this 3,500, there will be a developed ABX here because of ABY. So therefore, ABX here as computed is 6,062.18, that is towards left. So we need to counter that, and there will be no other force member to counter that than AC. So ABX now will be countered by an equivalent value of AC, which is also ABX equal to 6,062.18, and that should be equal to tensile force. So the next step is to choose another joint wherein it only involves two unknowns, so that we can work with summation forces X and summation forces Y. So looking at the truss, of course, it is obvious that if we are going to consider the joint here, and then there will be no force here, of course, no vertical force, therefore, we can say that this is a zero force member. Practically, we should move working with the joint B rather than joint C, because joint B here has two unknowns. Unlike on C, there will be three unknowns, namely BC, CD, and this one. So we move on to the joint B. This time, we have no choice but to isolate the joint and label the forces. So to isolate the joint B, we have to draw an X and Y axis. We have 1,000 going down, a compression AB inclined at 30 degrees with the horizontal, and computed to be 7,000. So aligned to this force member is BD, which I'm going to assume to be compression for a while. So perpendicular to these parallel members is BC, which I'm going to assume to be tensile. So this is BC, inclined at a certain angle. Of course, if this is perpendicular to this line, therefore we can just have the angle. If this is perpendicular or also, that is 60 degrees, and of course this is also 30 degrees. For our convenience, we can now place the computed components of 7,000. That is 3,500 and 6,062.18. Then we will perform summation forces vertical. We have negative 1,000 going down, negative BD sine of 30 degrees, upward 7,000 sine of 30, and downward BC cosine 30. So this shall be equal to 0. So of course, we can see in the equation that there are two unknowns. So for the meantime, we're going to arrange this wherein we have two variables on the left side and a constant on the right side. We just copy or retain BD and BC on the right side, and combining the constant, we have negative 2,500. So let this be our equation 1. For summation forces x is equal to 0, we have leftwards BD cosine of 30 degrees, rightwards BC sine 30 degrees, and another rightwards 7,000 cosine 30 degrees. All of these shall be equal to 0. So again, this equation is arranged in a manner with or complied with the arrangement of the first equation, so that we can easily determine the unknown variables. We retain BD and BC on the left side and transpose 7,000 cosine 30 on the other side. Let this be our equation 2. We have BD is equal to positive 65 and BC equal to negative 866.03. So 65 positive simply means we have a correct assumption on the direction of the BD. So BD is initially assumed to be compression. So we yielded to a positive answer. So this is really a compression orientation. So BC is initially assumed to be a tensile, and we yielded to a negative value. So we're going to correct BC is equal to 866.03. This is also compression. So moving on, let us review what we have got here. We have already gained BC and BD, so we're gonna place that in our truss. For BD, we have a compression equivalent to 6,500 pounds. That is in compression. For BC, we have also a compression equivalent to 866.03, which is also in compression. Finally, moving on into joint C. To complete this truss anyway, the left portion is symmetrical to the right portion. So we'll just have to adapt the forces on what we have solved in the left, because these are just symmetrical. So the remaining members here are CD and this one. So I'll just have to place here H. So for C, we will just need to determine the horizontal and vertical component of 866 so that we can solve for CD. So illustrating the triangle for 866.03, this is inclined at 60 degrees. We have here the BCX and the BCY. By function of cosine 60, this is equal to BCX all over 866.03. Hence, BCX is 433.02. By sine function, sine 60 is equal to BCY all over 866.03. Hence, BCY is 750. Knowing the values here, BCY and BCX, we can now proceed to isolate joint C. So at joint C, for summation forces X, we have a leftwards 6062. Okay, just place it here. So if it is a leftwards, that is negative 6062.18, plus rightwards 433.02, that is BCX. So before we proceed, CH and CD should have an assumed direction. So we just assume that CH is a tensile and CD to be compressive. We again draw the slope for CD so that we have CDX and CDY. So going back to this equation of summation forces X is equal to 0, we have negative CDX plus CH. All of those will be equal to 0. So here, we cannot continue yet because there are two unknowns here. Of course, looking at the vertical, I think we can observe here that there is only a single unknown for y, that is just the component of CD, y. So for this, we have actually downwards 2000 and a downward component of 866, or that is actually our BCY, and BCY is 750. Therefore, it is obvious that at joint C, the existing vertical forces are 750 and 2000, that will sum up to a downwards 2750. So therefore, it is obvious that we have assumed it to be tension, and it is assumed to be having a wrong assumption. So because 2000 is downwards and BCY is also downwards, and again that will sum up to 2750. So therefore CDY is 2750. By this we can also obtain CDX by considering the triangle of CD. So illustrating CD, we have a vertical to 750. We know the 60 degrees angle, and this is CDX. We can write tangent 60 is equal to 2750 all over CDX. So finally, CDX is equal to 2750 all over tangent 60. That is 1587.71. Therefore, we can now investigate what is the remaining force along X to be balanced by CH. So here we have a leftward 6062.18, and we have here a rightwards because we have a negative assumption here. So just remain or retain the direction but carry the sign, because this is a negative, because CDY in the first place is negative, y negative, because it is going against your assumed direction. Therefore, 6062.18, this is negative. We are going to add or minus negative 1587, or simply this will just deduct 6062.18 minus 1587. Of course, this leftward force will still prevail, so that will be the force on CH. So to avoid confusion, we shall write the equation for X at along C. So starting with 6062, summation forces along X is equal to 0. We have negative 6062.18 plus the component of 866.03, which is 433.02, minus negative CDX, which is 1587.71, plus CH is equal to 0. We have CH is equal to 4041.45, and this is tensile. So we can get also the value of CD. We have square root of 1587.71 squared plus 2750 squared. We have 3175.42. And from the figure, we can see that CD is negative. So it is assumed initially to be compression, and we have a negative, therefore it is in tension. So it should be tensile. Okay, so reviewing our results here, we have actually completed the forces. So we're just gonna place here the value for CH 4041.45, and the value for CD, just retain this direction but indicate that CD is negative 3175.42. So of course, if this is compression and that is negative, the direction is reversed. Okay, so this completes our analysis for this truss, and for the other side, just adapt these forces because it is symmetrically loaded. So thank you for listening, and I hope you have more practice on this. Goodbye.